Hi, so I'm going to do a lecture on energy, the work energy theorem and kinetic energy. Okay, so the first thing we're going to do is the work energy theorem. And this is, I'm sure, important for some of your problems and just kind of in general. And so what that tells us is, and we're going to use W for work. And I don't want to get that confused with the W that we use for weight, which is lowercase. It is kind of important to remember the variables that we use, we just kind of define. They won't always, as we use them, um, a lowercase w isn't always going to mean weight, uppercase W isn't always going to mean work, but that's what I'll use here. And then eventually I'll move to E for energy too. But we'll start out with the W there. And so basically it's going to be a scalar, and it's going to be the dot product of the force, which is a vector, and the displacement, which is also a vector. And if you know the rules for the dot product for a vector, that's basically the same thing as the magnitude. So I'll write this formally here. First, magnitude of F times the magnitude of the displacement times cosine theta. Okay, so what this is going to look like here is if I have two vectors, one vector for displacement, one vector for force, and then I have the angle theta there. What this means essentially is the work that we're going to do is, so you can see this, the adjacent angle to the theta is going to be along here. So the only amount of work that we're going to do is along the displacement, even though the force is not aligned with it. We do have another component here that won't count. Now, if the value of theta is equal to 0, which means that they're aligned, the force is aligned with the displacement the whole time, then this equation for work just goes to F times the displacement. Write a better D. Displacement. And so that's the same as writing delta X. And it's also the same as writing X minus X naught. Yeah. So the X naught or X sub 0, so that's your initial position. So it kind of makes sense wherever you are minus where you started. And a lot of times that might equal 0. A lot of times, sometimes it might not, but it's important. It's important for that fact that we don't always start at 0 as far as our position. Okay, so that's essentially the work energy theorem, is that the work is going to equal the force times the displacement. Now, to get to kinetic energy, actually I should write this here. This is the work energy theorem. Okay, so yeah, the kinetic energy is, we're just going to have to do a little bit of manipulation here. I'll go ahead and change this to a different color. So we know that F equals ma, pretty fundamental concept in this course, Physics 1, which is the acceleration. So we can substitute that in to our equation, and then we have W is going to equal M times A times D. So it spells out mad, but that's the mass times acceleration times displacement. A better way to write this, as you can see, is the way we had it before, which is x minus x naught. So this, hopefully this is kind of starting to look like an equation that we had from kinematics. And if we want to get the kinetic energy, which is going to be proportional to the velocity, then we're going to use this equation. I'll switch my color again. We're going to use an equation which is v squared equals v naught squared plus 2a times the quantity x minus x naught. So as you can see, that a times x naught is basically the same as there. So what we want to do is we're going to basically replace that and put that, replace for the acceleration. And then so A is going to equal v minus v0 over 2 times x minus x naught, or D. Actually, it's easier. I guess we'll just leave it that way. Either way. And I did skipped a few algebra steps for that, but we can put this into this equation, and I can change this again. What we used. We can use purple because this is important. Okay, so we have W work equals the mass, and we put in this for the acceleration, or A. Put in this for A, and so that's going to be, yeah, we'll just keep that in red. That's going to be v squared minus v naught squared over 2 x minus x naught, and then it should actually be all the way around. So do that, and then we have x minus x naught. And so you can see these cancel out here, basically, and so that could be D. And so up here, what this becomes is W equals M over 2. Here's a simple way to write it. V minus V naught. Okay, so that's essentially what we have. So I'm going to erase some of this. Erase this part. Erase this equation. Okay. And I'm going to write this same equation another way, which is work is equal to 1/2 m v squared minus 1/2 m v naught squared. Okay, so this is really important. This is going to be our change in kinetic energy. And that is, as you can see, so if we have initial velocity, we're going to have initial kinetic energy, and then as whatever v is at the point that we're measuring it, that's going to be that. So essentially this becomes our kinetic energy, and we can write, so for KE, we'll just, yeah. For some reason, drawing. KE is 1/2 mv squared. And that's going to be really important for this week. That's the kinetic energy. Okay. So, yeah, one little thing I wanted to add here, but actually I don't need to because it's, I would say when you do a higher level physics, you can also do this in terms of the momentum, which is, I can just write this here, which is for some reason it's not writing. Okay, Ke is equal to p squared over 2m, and so p is the momentum, and p is equal to m times v. So you can see that that would go to, if you put this in, Ke is equal to mv 20 squared over 2m. So that m cancels, and one of those m cancels, so then that's equal to 1/2 mv squared. And so I would say that's how, it doesn't tell you this in the book, but I thought that's kind of important because that's another way to write it. Okay, so that's all for the work energy theorem and the kinetic energy. I did do another video on the work energy theorem before, but hopefully that kind of spells it out and how we get there. And so our next video will be on potential energy. All right, thanks.